Good evening everyone. Good evening. I welcome you all again to the JEE Enthuse. Hope you guys are doing great. Well people, if I'm audible and visible to everyone, let me know in the chat box. Hi Dev, hi Sahana. Hello Aishwarya, good evening. Let me know in the chat box if I'm audible and visible to everyone. Yes. Hello Shreya. I'm doing great. How are you doing? I'm doing wonderful. Good evening, Dave. Good evening. Welcome to the session, guys. Welcome to the session. Well, as you all must be knowing, today we are going to do the chemical kinetics part 5, yeah? And we are continuing with the first order reactions which we started in the last session, okay? As you all must be knowing, in the last session we talked about the first order reactions. We talked about the integrated rate equation for the first order. We talked about half-life, completion time taken to complete 75% of the first order reaction, time taken to complete 87.5% of the first order reaction. Everything was done in the last session, and in the today's session we are going to continue with that only, yes, and we are going to talk about more characteristics of the first order reactions in detail, right? Okay. So before starting the session, let me introduce myself. As you must be knowing now, my name is Wassim and I'm your chemistry master teacher right here, okay? Alright, so people, this is the schedule of the week which I've been following, yes. And people, today it's going to be part 5 of chemical kinetics. Rest you'll be getting to know in the next session, yeah? Okay. So for the ones who have no idea about the Vedantu JEE 2021 crash course which we are starting on the actual Vedantu platform, let me tell you guys, on the actual Vedantu platform we are starting one crash course for the ones who are going to write the JEE in 2021. Okay, so what all benefits you guys are going to get right here if you'll enroll in this crash course? Let me tell you, we are going to cover your whole syllabus before your JEE 2021 examination, and we are going to personally train you for the upcoming JEE 2021 examination, right? In physics, chemistry, as well as mathematics, yes? And people, apart from the syllabus completion, there will be a lot of many sessions on the time management. There will be sessions on how to solve the questions in lesser time. Everything, every tips and tricks will be provided to you by means of which you can get good ranks in your JEE 2021 examination, okay? So do get enrolled in this. And how to get enrolled in this? Let me tell you, there is a link in the description box of the video. I want you guys to click on that link. Use the coupon code as WSCC21. On using the coupon code of WSCC21, you'll be getting 20% off. And if you want me to personally train you, use this coupon code right here. And people, let me tell you, the last batch for the JEE 2021 crash course will be starting on 8th of Feb. Okay, so do get enrolled in this one, right? If you want to get benefited, right? Good evening, Karthik. Good evening. Welcome to the session. All right, and for the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Okay, so people, this is the marathon series which we have started on this channel. As you all must be knowing, on Thursdays you have got the marathon session with the Shimon sir. On Fridays you have got it with Shreyas sir. I mean, the last day you had it with him. Correct? And on Monday, you'll be having the marathon session with me right here on this channel. Yes. And I'll be letting you know the timing, and that will be updated in the community post. You can check it over there. Yeah. Okay. Which chapter and what time? All right. So these are the things which we are going to cover in the today's session about the first order reactions. We are going to talk about the different characteristics of first order reactions. Few characteristics we talked about in the last session and few were left, and we are going to talk about those characteristics of first order reaction right here in this session, okay? And apart from that, we'll be talking about the rate constant for a first order gaseous phase reactions. And people, we will be doing some good questions right here which have been asked in your mains and advanced as well, okay? So without wasting a lot of your time, let's get started right here with the characteristics of first order reactions which we couldn't finish in the last session, okay? So let's get started with something really interesting right here. Understand what I'll say, okay? Let's say, guys, I have got a balanced chemical equation A gives B. Let's say it's one balanced chemical equation A gives B, and I'm assuming the order of the reaction is 1. I'm assuming this is a first order reaction, yes? And let's assume its rate constant right here is equal to K, right? I've got a first order reaction, a balanced first order reaction whose rate constant is K, in which A gives B, yes? right? Okay, now people have a look. We know at time t is equal to 0, the concentration of reactant is taken as A naught, the concentration of product will be 0, yes, correct? Now people, at any time t, the concentration of reactant left is represented by AT and concentration of product formed at time t is going to be BT, yes? Now if I use the integrated rate equation for the first order reaction, how it's going to be? It's simple, guys. I can write something like this. I can say K is equal to, rate constant is equal to 1 divided by T ln of A naught divided by AT, initial concentration divided by final concentration of reactant at time T, correct? Right? This is how I'll be writing the integrated rate equation for the first order reaction. And people, at the same time, if you remember, in the last session I told you, half-life for a first order reaction is equal to ln of 2 divided by K, correct? Now can I eliminate K from here? K is going to be ln of 2 divided by T half, yeah? Now people, just compare these two equations. K is equal to 1 by T ln of A naught divided by AT. K is equal to ln of 2 divided by T half, yes? So instead of this K right here, I can put the value. It's going to be ln of 2 divided by T half. Ln of 2 divided by T half will be equal to 1 divided by T. It's going to be ln of A naught divided by AT, correct? Now I'm going to get one important result right here, which I'll be using directly in the questions, by means of which you can solve the equations very, very easily right here. See guys what I'll be getting. I'll just shuffle the equation a bit. I'll be getting something like this. T divided by T half multiplied by ln of 2 is going to be equal to ln of A naught divided by AT. Yes, this is something which I got, correct? If I take this T by T half into the power of this 2, I can do that. I can write ln of 2 raised power T divided by T half. Raised power T divided by T half is going to be simply equal to ln of A naught divided by AT right here. Yes, correct? I can say that. Yes, can I do that? Absolutely, I can do that, right? Now people, this term, this T by T half, I'm writing this T by T half, I'm representing this T by T half by N right here, where N stands for number of half-lives. Now what is this N? You'll get the idea in some time, okay? So I can write it like this, ln of 2 to the power N, where N is the number of half-lives, is equal to ln of A naught divided by AT, correct? Now people, it's going to be simply equal to 2 to the power N is equal to A naught divided by AT, or I can say something like this, AT is equal to A naught multiplied by 1 divided by 2 raised power N. Yes, this is something which I can write. Correct? So this is one important expression which I want you guys to take a note of. Yes, and people, you have to be careful with the terminologies into this expression. What is this AT? AT is the concentration of reactant left at any time t. Yes, A naught is the initial concentration of reactant. N is the number of half-lives. Now what is that number of half-lives? Let's say the half-life of this first order reaction is 10 minutes. Let's say half-life of this first order reaction is 10 minutes. If I'm writing time t is equal to 20 minutes, can I say 20 minutes is going to be simply 2 half-lives? Yes. See, let's assume the half-life of this first order reaction is 10 minutes. If I've got the given time as 20 minutes, I can write N is equal to T divided by T half, which is 20 divided by 10. The value is going to be 2. So this 20 minutes, I can call it as 2 half-lives for the reaction, for the first order reaction, whose half-life is 10 minutes. Yes. So N right here represents the number of half-lives, which is equal to given time divided by half-life of the reaction, right? Now the point is how to apply this equation in the questions, how to get the questions easily done from the first order reactions. Yes? Right? Alright, Shreya, I'll be letting you know that at the end, okay? I'll be letting you know about that at the end. Yes, Gautam, you can let me know what about your doubt, bro? You can let me know that. Okay? Hi, Umar, how are you doing? Hello, Shahid. Okay, now people, see how this equation is to be used in the questions. Understand properly what I'll say. See guys, I'm given with the reaction right here. I'm given with the question right here, and as per the equation is concerned, rate constant for a first order reaction is given to me 1.386 minute inverse. Minute inverse is the unit of rate constant. That means the reaction whose rate constant is given to me must be of the order 1. Yes. Calculate the concentration of reactant left at time t is equal to 8 minutes. Calculate the concentration of reactant left at time t is equal to 8 minutes. Yes, this is the question which is given to me, correct? Now people, the first thing, I got to know the reaction is of first order whose rate constant is given to me, because from the unit of rate constant, I got to know the reaction is of first order, number 1. Number 2, can I calculate half-life of the reaction whose rate constant is given to me? Yes, since it's a first order reaction, so its half-life is going to be 0.693 divided by K right here. Yes. Correct. Now people, it's going to be simply equal to, I can write it as 0.693 divided by K value is 1.386. So I'll be simply getting the value of T half as 1 by 2. I got the half-life of the reaction as 1 by 2. Correct. Now people, can I calculate the value of N? N represents the number of half-lives. Yes, I can do that. Number of half-lives is going to be given time divided by half-life. Yes. T is given to you. Given time is given, right? Given time is 8 minutes. Divided by half-life is 0.5 minutes, or I'll say 1 by 2 minutes. Yes, half-life is 1 by 2 minutes, correct? So people, I'll be getting the value of the number of half-lives equal to 16 right here. I got the number of half-lives as 16. Yes, I got the number of half-lives as 16. What am I supposed to calculate? Concentration of reactant left after 8 minutes. The formula which I gave you right now, that was AT is equal to A naught multiplied by 1 divided by 2 to the power N. I can say AT. AT represents the concentration of reactant left after 8 minutes. It's going to be A naught multiplied by 1 divided by 2 raised power N value is 16, which I got. So this is going to be the concentration of reactant left after 8 minutes right here. Yes, and its units are going to be simply moles later inverse. So this is going to be initial concentration multiplied by 1 by 2 to the power 16. It's going to be the concentration of reactant left after 8 minutes, which we are supposed to calculate, right? Let me know in the chat box if it is clear to you. Let me know in the chat box if it is clear to everyone, so that I can move on to the next question. Let me know in the chat box. Yes, very simple one, yeah? You need to just remember this formula. You're done. Yes. Concentration of reactant left at any time is equal to A naught multiplied by 1 by 2 to the power N, where A naught is the initial concentration and AT is the concentration of reactant left at any time. And N is the number of half-lives, which is given time divided by half-life of the reaction. Yes. Correct? Exactly. Let's move on to the next one. Let's see if we can solve this one or not. See guys. What amount of reactant will be left after 3.5 minutes? That means given time is given to me, T value is given to me as 3.5 minutes. I need to check what amount of reactant will be left after 3 minutes, okay? And this is the curve which is given for a first order reaction. This is the curve which is given for a first order reaction. And the curve is given to me as ln of AT versus T, ln of AT versus T. People, as per our integrated rate equation of the first order, if you remember, ln of AT is equal to ln of A naught minus KT. Yes. Now I have plotted a curve between ln of AT versus T, ln of AT versus T. Can I say it's going to be of the form of y is equal to, see, I'm plotting ln of AT along y-axis and time along x-axis. So this term is basically y, this T over here is x. So this is going to be m, and this is minus, and this is c. Y is equal to minus mx plus c. It's a straight line. Yeah. So this is the curve which is given to me. Correct? Can I say slope of this curve is equal to minus k right here? Slope of this curve is equal to minus k right here. Yeah. Slope of this curve is equal to minus k right here. Right? I got the value of slope is equal to minus k. Now people, what is slope basically? Slope is tan of theta. So tan of theta right here is equal to minus k. What is theta? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. This is theta. Now first of all, I need to know what this theta is. People, if this is 45, this is 90, this is 45. Can I simply say it's going to be 135? Yes. So I can say tan of 135 is equal to minus k. Tan of 135 is equal to minus 1. So minus 1 is equal to minus k. So k value I got equal to 1. K value I got equal to 1 minute inverse. Yes. K value I got to know as 1 minute inverse. Yes. Correct. Now people, if we got the value of k, correct? If we got the value of k, can I calculate the half-life of the reaction? Half-life of the reaction is simply going to be ln of 2 divided by k. Ln of 2 is how much? Ln of 2 is 0.7. K value I got as 1. So half-life is given to me as 0.7. Yes. Half-life I got for the reaction as 0.7. 0.7 minutes I'll say. Correct? What am I supposed to check? What amount of reactant will be left after 3.5 minutes? Yes. So let me calculate the number of half-lives first. N is equal to T divided by T half. N is equal to T divided by T half. If you remember, T is given to me as 3.5. 3.5 divided by 0.7. Can I say it's going to be 5? So I got the number of half-lives as 5. Correct? Now people, what is the equation which I'll be writing? I'll say the concentration of reactant left after 3.5 minutes, which I'm representing by 80, is going to be A naught multiplied by 1 divided by 2 to the power n. Yes, I can write it like this. So it's simply going to be A naught divided by 2 to the power 5. 2 to the power 5 is simply 32. 2 to the 4 to 8 to 16 to 32, yeah. So this is the concentration of reactant left after 3.5 minutes, and its units are simply going to be moles later inverse, which I was supposed to calculate, right? Let me know in the chat box if it is clear. The concentration of reactant left after 3.5 minutes is going to be A naught divided by 32 moles liter inverse, yeah? Correct? Let me know in the chat box if it is clear. Yes? Wonderful, guys. Great. So let's move on and let's talk about one more important thing right here. One more important thing about the first order reactions from which questions have been frequently asked. Okay, what is that? Have a look. When the concentration of reactants at two different times are given, at that time, how do we calculate rate constant of a first order reaction? What do we mean by that? Understand it properly, what I'll be saying, because I'm going to use the same concept in the question after this. Okay, Umar, you can pull the video a little back. Just take the video a little back, pull the video a little back. It'll be automatically a replay. Okay. Okay, you can watch the replay, bro. That'll be awesome for you. Okay, let's say I've got a reaction as A gives B. Let's say this is the first order reaction which is given to me, whose rate constant is K. Let's assume that, right? It's a first order reaction. Good evening, Kamakshi. Good evening. Welcome to the session. Let's assume at time t is equal to 0, the concentration of reactant is A naught. The concentration of product will be 0. Yes. Let's assume at time t1, the concentration of reactant left is represented by AT1. Correct? Let's say at time t2, the concentration of reactant left is equal to AT2. Right? Correct? So people, at time t is equal to 0, the concentration of reactant was A naught. At time t1, in the time interval t1, you can say the concentration of reactant left is AT1, and in the time interval t2, the concentration of reactant left is AT2. Yes, people, if I write something like this, T2 minus T1, what is this T2 minus T1? First of all, T1 is the time taken by the reactant to change its concentration from A naught to AT1. T2 is the time taken by reactant to change its concentration from A naught to AT2. So what is T2 minus T1? T2 minus T1 is the time taken by reactant to change its concentration from AT1 to AT2. Yes, this is that time interval, T2 minus T1. Correct? T2 minus T1 is the time interval in which the concentration of reactant changes from AT1 to AT2. Yeah? Correct? Right? Now we will have a look on what I'll be doing now. Let me write the integrated rate equation in the time interval T1. Let me write the integrated rate equation for this time interval T1. I can write K is equal to 2.303 divided by T. Is it going to be divided by T, divided by T1? It's going to be divided by T1, yeah, time interval T1. And it's going to be log of A naught divided by AT. What is the concentration of reactant left at time T1? It's going to be AT1, yeah. AT1 like this, correct? If I write the integrated rate equation in the time interval T2 from A naught to AT2, yes, I can do that. I can write rate constant is equal to 2.303 divided by time interval, which is T2. It's going to be log of initial concentration A naught divided by what is the concentration of reactant left at time T2? It's going to be AT2, yes. It's going to be AT2, something like this, correct? Correct? I can do that, correct? Now people, what I'm simply going to do is, if I'll simply subtract these two equations, or we can do one thing, just write this T2 over here, write this K over here, just a second, 2.303 divided by K, correct? Similarly, just replace this T1 with this K, okay, and write T1 over here and write K over here, correct? Let's call this as equation number first, let's call this as equation number second. If I'll subtract second minus first, if I'm doing second minus first over here, what I'll be getting? I'll be getting T2 minus T1, 2.303 divided by K, I'm taking common. It's going to be 2.303 divided by K, yes. And now it's going to be log of this minus log of this, which is going to be log of this divided by this, yes. It's going to be simply log of A0 divided by AT2 divided by A0 divided by AT1. So this is A0, this is AT1. Yes, A0 got cancelled. So I'm getting something like this. Just shuffle this a bit. It's going to be K is equal to 2.303 divided by time interval T2 minus T1 will be equal. Sorry, it's not will be equal, multiplied by, yeah? Multiplied by what? Multiplied by log of concentration of reactant at time T1 divided by concentration of reactant at time T2. Yes, this is something very important which I'll be using in the questions which I'll be giving you in some time. Yeah. Now people, I can arrange this equation a bit nicely right here. Have a look. In another form, I mean, see, I'm giving you the first order reaction right here. This is the first order reaction which is given to me. And we know for a first order reaction, rate of reaction is equal to K multiplied by concentration of reactant to the power 1. Correct? If I write this expression at time T1, what it's going to be? I'll say rate of reaction at time T1, which I'm representing by R1, is equal to K multiplied by concentration of reactant A at time T1, that is AT1. Yes, it is AT1. Similarly, if I write the rate of reaction at time T2, it's going to be K multiplied by concentration of reactant at time T2. If I divide these two equations, can I get something like this? R1 divided by R2 is equal to AT1 divided by AT2. Yes. Now people, instead of AT1 by AT2, I can use the term R1 divided by R2 as well. Yeah, I can do that. Correct? Now I got one more expression which I can directly use in the questions. That's going to be K equal. That's going to be K is equal. Rate constant is equal to 2.303 divided by what? Divided by T2 minus T1. T2 minus T1 is the time interval in which the concentration of reactant changed from AT1 to AT2. Yeah. Multiplied by, it's going to be log of AT1 divided by AT2. Instead of that, I can simply write rate of reaction at time T1 divided by rate of reaction at time T2. This is one important expression which I got right here. And this expression I'll be directly using in the questions. One specific pattern of questions based on this expression. Okay, let's get to know what that question is all about, which we can solve from this expression or this expression. Yeah, let's get to know that. So I hope this is clear. Let's move on to the question in which I'm going to use this expression. See guys, the rate of the first order reaction is 0.04 mole liter inverse second inverse at 10 minutes and 0.03 moles liter inverse per second at 20 minutes after initiation. Okay, find the half-life of the reaction. So let's say I've got the reaction like this, A gives B. Okay, let's say at time T is equal to 0, the concentration of reactant is A0, okay? And this is, for example, 0, correct? Or let's not write the reaction, let's write the direct values. See guys, time T1 is given to me as how much? Time T1 is given to me as 10 minutes, yes? And at time T1 is equal to 10 minutes, what is the rate of the reaction which I'm representing by R1? That's given to me as 0.04, it's moles liter inverse second inverse. This is the rate of reaction after 10 minutes of the reaction, yes. Now similarly guys, at time T2, what is the T2 value which is given to me? T2 value is given to me as 20 minutes, yes. After 20 minutes, at 20 minutes, what is the rate of the reaction which I'm representing by R2? It's given as 0.03 moles liter inverse second inverse. Yeah, this is something which is given to me. What am I supposed to calculate? I'm supposed to calculate the half-life of the reaction. Yeah, I'm supposed to calculate half-life of the reaction. In order to calculate half-life of the first order reaction, what do I need? What do I have? What do I need? In order to calculate half-life of the reaction, I should have the rate constant value. Now people, if you can have a look right here, I'm given with the two rates of the reactions. I'm given with the rates of reaction in two different times, at two different times. I'm given with the rate of reactions at two different times. And few minutes back, I told you how to calculate a rate constant when two different rates are given at two different times. Yes. So what I'll be doing right here, I can simply say K is equal. It's going to be 2.303 divided by T2 minus T1 multiplied by what? Multiplied by log of R1 divided by R2. Yes. This is the expression which I'll be using. People, I've got everything which I need in this expression. K is equal. I can write something like this, 2.303 divided by T2 minus T1, which is going to be simply 10. Log of R1 divided by R2. R1 is 0.04, R2 is 0.03. It's simply going to be 4 by 3. 4 by 3 means log of 4 minus log of 3. Yes. So from this, I can get the value of K. So people, the value of K is going to be 2.303 divided by 10. Log of 4, as you all must be knowing, that is 0.6 minus log of 3 is 0.47. Now people, can you get the value of K from here? It is going to be 2.303 multiplied by, it's going to be 0.13 divided by 10. Correct? And what are going to be its units? Its units are going to be what? Second inverse. Yeah. Correct? Correct? I got the value of K. Now people, if you got the value of K, I can simply get the half-life of the reaction. Since the reaction is first order, it's going to be ln of 2. Ln of 2 is nothing, 0.693 divided by K. Correct? I have everything. I can use it in this equation. I can get the half-life of the reaction. It's going to be 0.693 divided by K value I got to know as 2.303 multiplied by 0.13 divided by 10, and that 10 goes up like this. Yeah. So it's going to be T half is equal. It's going to be 6.93 divided by 2.303. It's going to be 3 divided by 0.13. Just calculate it. Its value is going to come in seconds. This is going to be the half-life of the reaction, right? This is going to be the half-life of the reaction. Let me know in the chat box if it is clear to everyone. Let me know in the chat box if it is clear to everyone. Yeah? Let me know fast. Yes? Shreya is saying it's coming as 23. Is that Shreya? So the half-life of the reaction you are getting as 23 seconds from here. Yeah? Okay. Wonderful. Let's move on and let's talk about few more things. Okay. This is one more question on your screen and you can easily solve this one as well. Okay. See guys, as per this question is concerned, it is one nice question right here. These are basically two questions. Yeah. If 6.2 grams of NH2NO2 is taken, okay, calculate time taken to complete 99% of the reaction, right? Calculate the volume of dry N2O produced at STP, and we are given with the half-life of the reaction as well. Correct? We are given with the half-life of the reaction as well. Well, people, if you are given with the half-life of the reaction, can you calculate rate constant of this reaction? Yes. Can you calculate rate constant of this reaction? Rate constant of this reaction, I can write half-life is nothing. It is 0.693 divided by K. It's equal to 2.1 hours. So K is equal to 0.693 divided by 2.1. Okay. For the simplicity of the calculations, just take this value as 0.7. 0.7 divided by 2.1, which is 1 by 3. So I got the K value as 1 by 3 R inverse. Yes, for the reaction. I got the rate constant. Now people, what am I supposed to check? I need to calculate the time taken to complete 99% of the reaction. Right? How will I be solving it? Very simple. I can write it like this. I can say T is equal, time taken to complete 99% of the reaction will be equal to 2.303 divided by K. K value you got to know as 1 by 3. Yeah, K value is simply as 1 by 3. And it's going to be log of initial concentration of reactant divided by concentration of reactant left When 99% reaction is completed. And when 99% of the reaction will get completed, at that time I can say 99% of the reactant would have got converted into product. So at that time I'll be left with what? I'll be left with 1% of reactant. 1% of A naught will be left. 1% of A naught means 1 divided by 100 multiplied by A naught will be left. Yes, it used to be log of A naught divided by 80, and 80 is the concentration of reactant left when the 99% of the reaction will be completed. Yes, so A naught got cancelled, so that 100 goes up. It's going to be time taken to complete 99% of the reaction is going to be 3 multiplied by 2.303. It's going to be log of 10 to the power 2, which is going to be 2 log 10, which is going to be simply 2. Just calculate this value, you'll be getting the answer. Yes, this is going to be the time taken to complete 99% of the reaction, and the answer will be in hours. Yes, time taken to complete 99% of the reaction. You can let me know its exact value in the chat box. You can let me know its exact value in the chat box. Let me know fast, let me know fast. Is it coming as 13.8? Okay, so 13.8 hours will be the time taken to complete what? To complete 99% of the reaction which is given to us. Okay? Yeah? Wonderful, guys. Now the second part of the equation, how to do this? How to do this? Have a look. Volume of dry N2O produced at STP. We are supposed to calculate the volume of dry N2O which is produced at STP. This is the reaction which is given to me. This is the reaction which is given to me, correct? This is the reaction which is given to me, right? And people, initially I have 6.2 grams of NH2NO2. So how many moles of NH2NO2 I have? I can calculate number of moles of NH2NO2 in the beginning. It's going to be mass of this divided by molar mass of this, that is 62. The value is going to be simply 0.1. So initially I have 0.1 moles of this NH2NO2. Yes. So I can say at time t is equal to 0, I have got 0.1 mole of this. This is going to be 0. This is going to be 0. Correct? Now, since we got to know 99% of the reaction is getting completed. Yes. And when the 99% of the reaction is getting completed, what does that mean? That means 99% of the reactant is getting converted into products. So I can say I'll be left with 0.1 minus 99% of 0.1. So the reactant, the number of moles of reactant left in the container is going to be 0.1 minus 99% of the reactant has got converted into products. So 0.1 minus 99% of 0.1. But I've got nothing to do with this. What do I have to calculate? I have to calculate volume of dry N2O produced. Now people see, when 99% reaction will get completed, what can we conclude from that? That means 99% of the reactant is getting converted into products. Yes. Now we will use the stoichiometry. 1 mole of reactant gives 1 mole of this product. Yes. If 1 mole gives 1 mole, so I can say 99% of 0.1 will give 99% of 0.1 moles of N2O. So I got the number of moles of N2O which are getting formed. It is going to be equal to 99% of 0.1, which is 99 divided by 100 multiplied by 0.1, which is 1 by 10, or it's going to be 99 divided by 1000 right here, which is going to be 0.099 moles. So 0.099 moles of N2O are getting formed when 99% of the reaction is getting completed. Yes. Now people, am I supposed to calculate the moles of N2O formed, volume of N2O formed? I'm supposed to calculate volume of dry N2O produced at STP. I got the moles of N2O which are getting formed right here. Yes. And we know at STP, how do we convert moles into volume? I simply need to multiply this term by 22.4. So volume of N2O produced at STP is going to be number of moles of N2O produced multiplied by 22.4 liters. Yes. It's going to be 0.099 multiplied by 22.4. The value is going to be in liters. So this much volume of N2O will be liberated at STP when 99% of the reaction would have got completed. Yes. Let me know in the chat box if it is clear to everyone. Let me know in the chat box if it is clear to everyone. It was a nice question. I hope you got it. Yes. Let me know in the chat box so that I can move on to one more. Okay, it's coming as 2.21 liters. Shreya is saying it's coming as 2.21 liters, all right. So 2.21 liters of N2O gas is getting liberated when 99% of the reaction would have got completed over here. Yes, yes, a very, very simple and ordinary question this was, yeah. Let's move on to one more. Let me see if we can solve this one or not. It's again a nice question, guys. You can easily solve this one as well and see how to approach to this sort of a question. In what time will the molar ratio of ethylene to cyclobutane be 1? Okay, we need to check at what time the molar ratio of ethylene to butane, to cyclobutane will be equal to 1. Yes, that's what we need to check. That's what we need to check. And we are given with the rate constant value as well. People, if we are given with the rate constant value, can we calculate its half-life? We can calculate its half-life. But I've got nothing to do with the half-life right here. Okay, so how to approach this sort of equation? See, I'm writing the reaction again. It's C4H8. C4H8, it gives what? It gives 2 times C2H4. 2 times C2H4, correct? Let's say initially at time t is equal to 0, I have got A moles of this reactant, this is going to be 0. Let's assume X moles I've got at time t. Let's say at time t, X moles I've got converted into products. So I'll be left with A minus X moles of reactant. Since 1 mole gives 2 moles, so X moles will give me 2X moles right here. So I'm assuming at time t, the number of moles of reactant left is A minus X. The number of moles of product formed is 2X. Yes? This is something which I got right here. Correct? And I'm assuming at time t, the molar ratio of these two is becoming 1. I'm assuming at time t, let's assume at this time t, the molar ratio of ethylene to cyclobutane is equal to 1. Correct? I'm assuming the molar ratio 2x divided by A minus X is equal to 1. At this time, I'm assuming the molar ratio is equal to 1, and I need to calculate this time value. I need to check at what time their molar ratio becomes equal to 1. Yeah. Correct? What can I conclude from here, guys? Can I say 2x is simply going to be equal to A minus X? Yeah, 2x is equal to A minus X. Or can I say x will be equal to A divided by 3 from here? I got the value of x right here. I got the value of x right here. Correct? Yes. I'm given with the rate constant value. I'm given with the rate constant value. I can use the simple integrated rate equation. I can use the simple integrated rate equation for the first order kinetics. Correct? That is going to be equal to T is equal to 2.303 divided by K. K value is given to us as 2.3 into 10 to the power minus 4 log of A naught divided by AT. A naught was the initial concentration. A naught was the initial concentration, and instead of concentration, I'm directly using moles right here. So initial moles divided by initial moles of reactant divided by moles of reactant left at time t, which is A minus X. So it's going to be A minus X value. I got to know that's A by 3. Yes, we are done with the question almost. I can get the time right here. This and this approximately will get cancelled out. So it becomes 10 power 4. It becomes log of A divided by 2A divided by 3. Yes, 2A divided by 3. That 3 comes up. This A and this A got cancelled. So time value, I got to know 10 power 4. It's going to be log of 3 divided by 2, which is going to be simply log of 3 minus log of 2. Yes, so T value will be simply 10 power 4 multiplied by log of 3. All of you must be knowing that is 0.47. Log of 2 is 0.3. So the value is going to be simply equal 0.14. Yeah. Yes, sorry, 0.17 into 10 to the power 4. And its units are what? Its units are seconds. Yes, so you can say it like this. You can say it like this. In 1700 seconds, after 1700 seconds, I can say at t is equal to 1700 seconds, the molar ratio of these two will be equal to 1, which I was supposed to calculate. Let me know in the chat box if it is clear. Let me know in the chat box if it is clear to everyone. I hope you got this question. Yeah? Correct? So this time I was supposed to calculate the time at which the molar ratio of ethylene to cyclobutane will be equal to 1. So at 1700 seconds, the molar ratio of ethylene to the cyclobutane will be equal to 1, which is what I was supposed to calculate, right? Yeah? Exactly, guys. Now one more thing. One more question. This is the question which you guys are going to let me know in the chat box, okay? Solution of this question, answer of this question, you guys are going to let me know in the chat box. It's a very simple question, but there is one important concept involved in this, okay? There is one important concept involved in this, right? So do this question and let me know the answer in the comment box afterwards. You can take the screenshot of it. Just take the screenshot of it. Yeah, done? Okay, let's move on to one more concept then, which is the rate constant of a first order gaseous phase reaction, rate constant of a first order gaseous phase reaction. Again, a very important concept and very simple also, okay? But little bit of calculation is needed in this question right here. How do we write the rate constant for the first order gaseous phase reactions? Understand properly what I'll be saying, okay? Let's say, guys, I've got a reaction as A gives B plus C. And I'm assuming this A, B, and C, all the three are right here in gaseous phase, okay? And I'm assuming it's a balanced chemical equation where the stoichiometric coefficients are 1, 1, 1, rate constant is K, and it's a first order reaction. I'm assuming all this, okay? I'm assuming all this, right? Now, people, this reaction will be taking place in some container, yeah? And at time t is equal to 0, there will be only a reactant in the container, correct? So whatever will be the total pressure in the container, whatever will be the total pressure of the container at time t is equal to 0, that is going to be only due to A, since there will be no B and no C at time t is equal to 0. Yes. Let's say the pressure due to A at time t is equal to 0, B P naught, this is going to be 0, this is going to be 0. Yes. Now I'm going to treat this pressure in the same way as moles. I'm going to treat this pressure in the same way as moles. Yeah. Let's say at time t, it is going to be P naught minus X. This is going to be what? This is going to be X. This is going to be X. What is this P naught minus X? This is the pressure of A at time t. The pressure of A at time t is X. The pressure of B at time t is X. The pressure of C at time t is again X. Yeah. If I ask you, okay, or let me not ask you anything right now. I'll be asking you that in some time. Okay. When the reaction proceeds, can I say there will be a time I can write time t is equal to infinity? Time t is equal to infinity, because we know a first order reaction never undergoes never undergoes 100% completion. We know that, yeah? We have seen that in the last session, if you remember. Let's assume at time t is equal to infinity, there will be no reactant in the container, so the pressure due to reactant will be 0. So entire reactant will have got converted into products at infinity. Yes, I can say 1 mole gives 1 mole, so P naught is going to give P naught, and this also going to be P naught. Yes, correct. Now we will understand. What is the initial pressure of the container at time t is equal to 0? That is P naught. What is the total pressure of the container at time t? That is going to be P naught minus X plus X plus X. So total pressure of the container at time t, I'm representing by PT. It's going to be P naught minus X plus X plus X. It's going to be simply P naught plus X. Correct? What is the total pressure of the container at infinity, which I'm representing by P infinite, which is simply going to be equal to twice P naught. Yeah, I hope you got it. I hope you got it till now. Very simple, guys. P naught is the initial total pressure of the container. PT is the total pressure of the container at time t. P infinite is the total pressure at the completion of the reaction. Yes. Now, people, I need to write the rate constant for this reaction. I can write the rate constant in two forms. I can write the rate constant in two ways. Yeah. I can write the rate constant either in terms of P naught and PT, or I can write the rate constant in terms of PT and P infinite. Okay. For example, I need to write the rate constant in terms of P naught and PT. How will I be writing that? Understand right here. Understand what I'll say. From here, guys, can I say the value of X will be PT minus P naught? This is the value of X which I got. Correct? Since it's a first order reaction, I can simply use its integrated rate equation. K is equal to 2.303, just a second, 2.303 divided by T, and it's going to be log of initial concentration of reactant, but right here I'll be using the initial pressure of reactant, divided by concentration of reactant at time t, but right here I'm going to use the pressure of reactant at time t, which is P naught minus X. And what is X? X I got to know as PT minus P naught. Yeah, PT minus P naught. So people, this is how we write the integrated rate equation for this first order reaction whose stoichiometric coefficients are 1:1:1 in terms of P naught and PT. It's going to be log of P naught divided by what is going to be? It's going to be P naught plus P naught, which is going to be twice P naught minus PT. You're not supposed to remember this expression. You should know how to form this expression. Yes, this is the expression of rate constant for a gaseous first order reaction, which is this one, okay, in terms of P naught and PT. Yeah, correct? I hope you got it. Now, people, I'm going to do the same thing, but in terms of PT and P infinite. This is the expression of rate constant in terms of P naught and PT. Now I'm going to write the same thing. I'm going to write the same K expression in terms of PT and P infinite. How will I be doing that? I hope this clear. I hope this clear. Let me erase this part. Let me erase this part. Let me erase this part right here. People, we know at infinity, the pressure due to A will be 0, correct? The pressure due to B will be P naught. The pressure due to B will be P naught. And I told you in the beginning, the total pressure at the completion of the reaction, which I'm representing by P infinite, is going to be simply 2 P naught. And people, this P naught is nothing. It is P infinite divided by 2. Yeah, P naught is equal to P infinite divided by 2, correct? Correct. Now people, if I write the integrated rate equation again for the first order gaseous phase reaction, isn't it going to be 2.303 divided by T? It's going to be log of initial concentration of reactant. Instead of that, I'm writing initial pressure of reactant divided by the concentration of reactant left at time T, which is this one. But right here, I'm going to use the partial pressure of reactant left at time T, which is P naught minus X. But now I'm going to write the expression of K in terms of what? In terms of PT and P infinite. So I don't need these P naught values right here. Okay, I need to eliminate these P naught. Now how will I be eliminating these P naught values? I can say K is equal to 2.303 divided by T. It's going to be log of P naught. People, instead of P naught, can I write P infinite by 2? It's going to be P infinite divided by 2 whole divided by. Instead of P naught, as I told you, P infinite divided by 2 minus X key value. We know that is PT minus P naught. I'm going to write it as PT minus P naught. P naught is nothing. P infinite divided by 2. Yes. So people, I'll get one more expression right here, and you're not supposed to remember that expression. I'm just showing you how to make these expressions. Yeah. And you need to know how to make these sort of expressions. So I got the rate constant K in terms of PT and P infinite. It's going to be equal to 2.303 divided by T, it's going to be log of, I'm writing P infinite divided by 2, P infinite divided by 2, P infinite divided by 2. This is P infinite by 2, this is P infinite by 2. That means I got P infinite minus PT. This is P infinite minus PT. Yes, this is the expression for the rate constant of this gaseous phase reaction in terms of P infinite and PT right here. I hope you got it. Yes, correct. Now people, how to solve these sort of questions? This was the general procedure which I've shown you right here, okay? And in this reaction, I have used the stoichiometry as 1:1:1. Stoichiometry can be anything, and by means of that stoichiometry change, every whole procedure will get changed. Yes, procedure will remain same, just the values will be changed. Now let me show you certain examples as well. I hope this is clear to everyone. See guys, this is one question which is given to us. And what are we supposed to calculate in this? Calculate the rate constant in terms of first P naught and PT, second PT and this is P infinite. PT as P infinite, yeah? These are the two questions which are given to me. And how do we approach to these sort of questions? Over here, the stoichiometry is not 1:1:1. So the values will get changed right here. And how the values will get changed, I'll be showing you that, okay? See guys, I'm giving you the reaction, the gaseous phase reaction, 2A gas. It gives what? It gives 3 times B gas plus what? Plus 4 times C gas. Yeah. This is the gaseous phase reaction which is given to me. And I'm assuming this has to be a first order reaction. This is a first order reaction. Yeah. This is a first order reaction whose rate constant is K, which I'm assuming. Yeah. So people, at time T is equal to 0, let's say the pressure due to A was P naught. This is going to be 0. This is going to be 0. Yeah. I'm going to solve the first part of the question. Right now. I'm going to write the K expression in terms of P naught and PT. Now see how I'll be doing. Let's assume at time T, what is going to be the pressure due to A at time T? What is going to be the pressure due to B at time T? What is going to be the pressure due to C at time T? How do I get that? In order to get that, I'll be treating these pressures same as that of moles. The way I used to treat moles, in the same way I'm going to treat the pressure. I'll be using the stoichiometry of the reaction. Very simple. Let's assume this is P naught minus X. Yeah, at time T. See guys, 2 moles gives 3 moles. So 1 will give 3 by 2. So X is going to give 3 by 2X. Correct? So people, this is the pressure due to B at time T. Similarly, you can let me know the pressure due to C at time T. You can let me know that as well. Okay, how? By using the stoichiometry again. 2 moles gives 4 moles. 1 mole gives 2 moles. So X moles are going to give me 2X moles. But these are not moles. This is the pressure due to C at time T. Yeah. If I ask you, what is the total pressure of the container at time t is equal to 0? Total pressure of the container will be P naught, because at time t is equal to 0, there is only A in the container and the pressure due to A is P naught, yeah? Total pressure, initial total pressure is P naught, correct? What is the pressure of the container at time t? What is the pressure of the container at time t? Can you let me know that? It's going to be at time t, the total pressure will be equal to P naught minus X, plus 3 divided by 2x plus 2x. Yes, this is going to be the total pressure at time t. Total pressure of the container at time t, correct? Now people, I can do something like this. Can I write like this? Pt minus P naught is equal. I can take 2 as the LCM. It's going to be minus 2x. It's going to be 3x. It's going to be 4x. I just took the LCM, correct? So it's going to be Pt minus P naught will be equal. This is going to be what? This is going to be x plus 4x is 5x. It's going to be 5x divided by 2. People, can I get the value of x from here? Can I say x value is going to be 2 divided by 5 multiplied by Pt minus P naught? I got the value of x, right? I got the value of x. This is the value of x which I got. Correct? This is the value of x which I got. Yes? Now guys, understand. I need to write the rate constant in terms of P naught and Pt. It's simply going to be equal to 2.303 divided by K. It's going to be log of initial concentration of reactant. Instead of initial concentration of reactant, I'm using the initial pressure of reactant, which is P naught, divided by it used to be the concentration of reactant left at time t. Now I'm going to use the pressure of reactant left at time t, which is P naught minus x, and x already I have told you how much that is. X value I have got to know, just a second. X value I've already got to know, that is 2 divided by 5 multiplied by Pt minus P naught. Yes, I need to do a bit of calculation. I got the rate constant, yeah. I got the rate constant in terms of what? In terms of P naught and Pt, which I was supposed to calculate. People, just a second. This is T right here, yeah. This is T right here. So K value right here I'll be getting as 2.303 divided by T. It's going to be log of P naught divided by. It's going to be P naught minus 2 divided by 5 Pt plus what? Plus P naught. And at the end, what you'll be getting? At the end, you'll be getting something like this. Let me erase this part over here. Let me erase this part over here. Yes, let me erase this part. You are getting the rate constant expression which I was supposed to calculate in terms of P naught and Pt. K will be simply equal to 2.303 divided by T. It's going to be log of P naught divided by, this is P naught plus P naught, twice P naught. So it is twice P naught minus 2 divided by 5 Pt, minus 2 divided by 5 Pt, correct? So people, I hope this is clear to everyone. Or I can write it like this: 5 2s are 10 minus 2 Pt divided by 5. It is 5. This you can replace this right here. You can write as 10 P naught minus 2 Pt. This is the expression of K in terms of P naught and Pt, which I was supposed to calculate as per the question. Let me know in the chat box if it is clear to everyone. Let me know. Then I can do the next part of the question. Then we can start the next part. Yeah. This is going to be the value of K. This is going to be the expression of K in terms of P naught and Pt. Yes. Now people, can you do the same thing in terms of Pt and P infinite? You can do the same thing, I believe. Yeah. How do we do that? I'm going to do it fastly. Rest the calculation part you can do on your own. People, and you're going to let me know the answer of the homework question as well. Okay, once the session ends. Once the session ends, do let me know the answer of the homework question which I gave you. Correct? Okay. Now we will see, have a look. Can I say at time t is equal to infinity, when we assume the reaction is 100% completed, which never gets completed experimentally, right? So I can say at time t infinite, can I say there'll be no reactant left, so the pressure due to reactant will be 0, yeah? Now use the stoichiometry. 2 moles gives 3 moles, 1 mole gives 3 by 2 moles, so P naught will give 3 by 2 P naught. So this is going to be the pressure due to B at time t is equal to infinity. Yes, when I assume 100% of the reaction is completed, yeah, theoretically. Okay, similarly guys, 2 moles gives 4 moles, so 1 will give 2, P naught will give twice P naught. Can you let me know what is going to be the total pressure of the container at at the completion of the reaction, which I'm representing by P infinite, it's going to be 3P naught by 2 plus 2P naught. It's going to be 3P naught plus what? Plus 4P naught, which is going to be 7P naught by 2. 7P naught divided by 2. Or people, I can write the P naught value in terms of P infinite. It's going to be 2 times P infinite divided by 7. Yes, I got the P naught value in terms of P infinite. Correct? What am I supposed to do? I'm going to write the expression of K in terms of PT and P infinite. I can do that now. I think it's almost done. It's almost done. Now people, let me write the integrate rate expression. It's going to be K is equal to 2.303 divided by T. It's going to be log of initial concentration, that means initial pressure of reactant divided by pressure of reactant left at time T, which is going to be P naught minus X. P naught minus X. Yes. Now, but I need the value of K in terms of PT and P infinite. I do not need these P naught terms right here. Yeah. Hi Kishan, welcome. Yes. Now what I'll be doing right here, I can say K is equal to 2.303 divided by T. It's going to be log of P naught. Instead of P naught, I can write 2 by 7 P infinite. I can write 2 divided by 7 multiplied by P infinite divided by, what is P infinite? P infinite is the total pressure of the container at the end of the reaction. Yes. Instead of P naught, again I'm writing 2 by 7 P infinite minus X. We have already got to know X value. We already got to know what is that? X value we already got to know, that is 2 divided by 5 multiplied by PT minus P naught. And instead of P naught, again I'm going to write 2 by 7 P infinite. Yes. People, can you solve this one a bit and you can let me know the value of K, the expression of K. You can make it in terms of P naught, I mean P infinite and PT right here. I hope this is clear to everyone. I hope this is clear to everyone. Let me know in the chat box if it is clear to every single guy. Yeah. Let me know in the chat box fast. Shreya, where did I do that? Where did I do that? Oh, in the previous question, maybe. You can change that a bit. That might be a calculation mistake or something. If that is. Yeah? Hello Puranam, welcome to the session, Okay, so people, yeah, I got it, Shreya, I got it. You can change the value, no issues. Hi Murugeshan, hello, hi Ankit, what's up guys, how are you doing? Alright, so people, this was all about the characteristics of the first order reaction and how do we write the rate constant of a gaseous phase reactions, okay? And a lot of questions also, and the homework which I gave you, I want all of you to give it a try and let me know the answer of that question in the comment box afterwards, okay? So people, this was all from my side in the today's session. I hope you're clear with the first order reactions now. I'll be meeting you guys day after tomorrow, and day after tomorrow is going to be the marathon session in which that is going to be one shot. Basically, in that one shot, we'll be finishing some of the chapter. Either it's going to be thermodynamics, or it's going to be equilibrium, or it's going to be states of matter, or it's going to be redox, okay? Yeah? Or it's going to be a solid state, correct? Shreya, I'll check that out and I'll let you know, okay? I'll check that out, why that Telegram channel link is not working. Let me talk to the operational team about it, okay? I'll get back to you in the next session, okay? So people, see you day after tomorrow. Till then, you guys take care. Bye-bye. God bless you all. Love you all. And stay safe. Do prepare. Hardcore. Take care. Bye-bye.